once chylomicrons have carried the triacylglycerols that you eat from your duodenum to your tissues, a lipase breaks it down into the glycerol and the 3 fatty acids that were on that triacylglycerol. Now the glycerol gets broken down in its own pathway represented in a previous video. In this video, we're going to talk about what happens to the fatty acids. How are the fatty acids broken down? Now, if you remember from the video on how pancreatic lipase breaks down triacylglycerols to give you the glycerol and the fatty acids, when the fatty acids leave, they leave as an acyl-CoA. So the fatty acid is this acyl group here with this whole thing. Oops. A fatty acid would normally just have an H attached to this oxygen here, but after it is broken apart using a lipase, instead of an H, you have a CoA there, and that's really just a good leaving group. So this whole big thing is really just a good leaving group because sulfur is a very big atom. So this is what our fatty acid looks like after the triacylglycerol is taken apart by a lipase enzyme. Now, the glycerol goes to the liver, but this fatty acid goes to the mitochondria, and it's going to be broken down by something called the beta-oxidation pathway. Now, this occurs in the mitochondria of your cells, but it's the beta-oxidation pathway. So let's explain that for just a second. First, the beta. If you look at this, we sort of zoom in on that fatty acid there. We have the carbonyl carbon, the carbon that's in the double bond to the oxygen. Next to that is called the alpha carbon, and next to that is called the beta carbon. So this right here is the beta carbon. Ultimately, to break this long chain of carbons down, it will ultimately get broken down to carbon dioxide and be exhaled out. But ultimately, to break this long chain of carbons down, we are going to need to put a double bond to oxygen on the beta carbon. The whole process takes 4 steps that we'll go through one at a time. The first step is to create a double bond between the alpha and beta carbons. Then you use that to add an OH onto the beta carbon. So notice we're putting an oxygen on the beta carbon, beta-oxidation. Then we turn the alcohol, we oxidize that into a carbonyl, and then finally we cleave this here. We cleave that bond there, so this gets exhaled. Notice, or that leaves. That's going to end up leaving as acetyl-CoA. Notice there are 2 carbons there. That'll enter the citric acid cycle and ultimately be exhaled out as carbon dioxide, and then the whole process can start again with this, because this will ultimately look like this here. So in order to break this down, we have to put an oxygen on the beta carbon, the carbon that's not next door, but one more away from the ester carbon, the carbonyl carbon of the fatty acid. And because you have to put an oxygen on that beta position, this whole process is called beta-oxidation. So in the mitochondria, the process that takes a fatty acid and breaks it down into something that can enter the citric acid cycle is called beta-oxidation. Okay, first, let's talk about how to make that pi bond, that degree of unsaturation between the alpha and the beta carbons. Now to do that, we're going to need a couple things. So let's take our acyl-CoA, our fatty acid really, and we're going to need FAD. FAD stands for flavin adenine dinucleotide, and just like with all of these big biological molecules, notice that there are parts that are going to be active and there are parts that are not going to be active. In this mechanism, this adenine with the ribose sugar and the two phosphates. Just like in other biological molecules, that is not the active part here. That's sort of something that controls solubility and makes sure it fits into the right enzymes, it's easy to produce, etc. But it's not going to be involved so much here. We're going to see a little action in this small sugar ring, and we're going to see some oxidation reduction action in this ring down here. Okay, the sugar ring, by the way, is called ribitol. So this is ribitol. And then this down here, the oxidation reduction part, is called flavin. The whole thing is flavin adenine dinucleotide. Okay. So the first thing that's going to happen is this acyl-CoA needs to fit into our enzyme, and that is actually the second thing we need. The enzyme we're going to use is acyl-CoA dehydrogenase. So notice you're going to be taking these long names of enzymes are long because they're really complete descriptions rather than just names. So we're going to take acyl-CoA, right? That's what we have here. This big thing is acyl-CoA, and we're going to take some hydrogens off of it. We're going to take a couple hydrogens off of this, and when we do that, there's going to be room to put a pi bond there. That's going to be our first step in breaking this fatty acid down. So acyl-CoA dehydrogenase, you take hydrogens off of acyl-CoA. It ends in ASE, so you know it's an enzyme. It's going to be speeding up the reaction, catalyzing the reaction without getting used up itself. Notice also conceptually what we're doing. By putting a pi bond here, a pi bond is an area of extra electrons. And when you have extra electrons, that's a place where the molecule can react. So by creating a pi bond there, we're making this part of the molecule reactive. And that's going to ultimately allow us to cleave that bond to break this up into smaller carbon chains. Okay. So the first thing that happens is this acyl-CoA gets positioned, gets positioned into the enzyme pocket. And one of the things that does that helps it to do that, are hydrogen bonds. So one of the crucial hydrogen bonds is a hydrogen bond, and it's going to be a little awkward here to get the right angle, but I'm going to do this. Now in this two-dimensional diagram, these look a little far away, but actually they're close in the enzyme pocket, and what we can do is take one of these H's, and let's think about what's happening there. The oxygen is very electronegative, pulls electrons to itself, becomes slightly negative. The hydrogen there loses that electron density, becomes slightly positive. Similarly, the oxygen of this carbonyl is slightly negative, pulling electron density to itself. And let me just get rid of this for a second. I'm just gonna, just so that's not as distracting. And I'll just put FAD here, so we remember what that is. But notice that this hydrogen is slightly positive, this oxygen slightly negative, and a hydrogen bond. Notice that's a misnomer, it's not an actual bond. A hydrogen bond is around 30 times weaker than the average covalent bond. But a hydrogen bond, an electrostatic attraction, an intermolecular force, can attract those two atoms and sort of hold them together. That helps to hold the acyl-CoA in place in this enzyme pocket. So that's one of the first things that happens. Remember, this little sugar part of FAD is called ribitol, and so it's one of the hydroxyl groups on ribitol that interact with the carbonyl oxygen of the acyl-CoA to hold that in place. Now, at the same time that that's happening, one of the amino acids in our enzyme, specifically the 376th amino acid, which is glutamate, so at position 376, we have this glutamate here, And that is going to take a hydrogen off of the alpha position of this fatty acid. Now remember something about the alpha position. So here, remember, we have the carbonyl carbon. This is the alpha carbon. This is the beta carbon. So this carbon here is the alpha carbon. And remember a crucial thing about the alpha carbon. The hydrogens there are acidic. Now there are two there. Those hydrogens are acidic because if one of them gets taken away, the electrons in that bond can snap back onto that carbon, and normally that would be extremely unstable. That carbon would have a full negative charge. Carbon is not either very big, so it can't dilute the charge, and it's not very electronegative, so it can't pull that charge close to the protons in the nucleus to help to stabilize it. So normally this would be really unstable. However, notice that there's resonance here. Because this is of this alpha position, that lone pair is actually allylic to this pi bond. So this can exist in a p orbital that's parallel with the two p orbitals in this pi bond. That allows that lone pair with its charge to spread out over all three of those atoms and to stabilize it. In other words, a hydrogen can leave this alpha position because the lone pair that's left behind can be stabilized through resonance. So because this hydrogen can be donated, it's acidic. An acid is a molecule that donates a hydrogen. So that alpha position is acidic. Now it does need something to pull the hydrogen off, and that's what the glutamate of our acyl-CoA dehydrogenase is going to do. So the oxygen here with a negative charge, the lone pairs on there, is going to rip this hydrogen off. And for a brief second, we're going to get an intermediate. So those electrons can snap back onto the alpha position. Let me just draw that a little more clearly. So those electrons snap back onto that alpha position. And so here, this charge is going to go away. Those bonding electrons, those lone pairs are going to become a bond. That lone pair is going to become a bond to this hydrogen. Oops. Hydrogen does not take these electrons. Those electrons snap back onto that carbon to form a lone pair, which has that negative charge. But because that's on an alpha position, that negative charge is stabilized through resonance like we saw before. It's diluted, spread out over all three of those atoms. Okay, now this here, what we have here, what we've turned our acyl-CoA molecule into, is something called a thioester. This is called a Thioester Enolate Ion. Remember that an ester is when you have a carbon double bonded to an oxygen, single bonded to an oxygen bonded to another carbon. So this is like the motif for an ester, a normal ester. But if you notice here, instead of a carbon on the other side, we have a sulfur. And the prefix for sulfur is thio. If you might remember that sulfurs are thiols, can be thiols. So this thio prefix is saying, on the other side, instead of a carbon, on the other side of this ester, instead of a carbon, we have a sulfur. So it's a thioester. An enolate, first en says you have a double bond, which we have right here. The enolate is telling you that you have a lone pair allylic to that en double bond. And it's an ion because it has that charge. So this is a thioester enolate ion. Now, this is not especially, it's stabilized by the resonance, but it's not something that's going to exist for too long. This is an intermediate. And so this is going to be stabilized ultimately by reaction with the flavin part of FAD, a flavin adenine dinucleotide. Now remember that we're trying to create a bond between the alpha and the beta carbons here. So the alpha and the beta carbons here. We have the electrons to do it. These electrons right here would love to go there, but we need something to leave to make room for that to happen. So something has to leave the beta carbon here. It has 4 bonds already. Something has to leave in order to allow this lone pair to move in and form a pi bond between the alpha and beta carbons. And that's what FAD is going to be doing. It's going to be removing one of these hydrogens. It's going to be letting one of those hydrogens be a leaving group. And so, but when that leaving group leaves, you have the room on that carbon to make the pi bond. Now, ultimately, this is going to happen through another, and I know that visually this is a little tricky, but this is going to happen through another interaction with the acyl-CoA dehydrogenase enzyme. This is the symbol for an acid, so A for acid, and then this is the hydrogen that acid is going to be giving up. Now I know that this is visually far away, but in the enzyme pocket, this acid is going to be close to this nitrogen right here. And so what we're going to do is we're going to have a sort of push and pull happening all at the same time to make this next part of this reaction happen. A push and pull of electrons that both together cause a flow of electrons. On the one hand, because this nitrogen is close to this acid here, the lone pair on that nitrogen is trying to steal that hydrogen, and the electrons would snap back onto that acid there. So that's a pull. On the other hand, now if that happens, one thing that sort of frees up is this nitrogen would get a positive charge. Now that would attract these electrons here. And so you can see how we're sort of pulling the electrons along. If those move, now there's a positive charge here. That would move these electrons over here. But now there's a positive charge here. And by creating that vacuum, and so let me draw these in one at a time. If we move this acid hydrogen, onto the nitrogen of FAD, that would then have a positive charge. And so it pulls these electrons over. So though that pi bond can become a lone pair, that neutralizes that positive charge. But now this carbon has the positive charge. So that pulls these electrons over. And now we have a pi bond here. And that positive charge is taken care of. But now the nitrogen is missing its electron. So it would have a positive charge. And that creates the sink that pulls one of these hydrides away. Remember, a hydride is a hydrogen atom with 2 electrons attached. And so both of these electrons with the hydrogen atom can go and attach themselves to the nitrogen. So that nitrogen then would have the hydrogen on it. Now notice we've put 2 H's onto the FAD, so now it's turned into FADH2. And notice also this carbon is missing electrons, right? If everything stayed as it was, this would have a positive charge. And so that opening, that pull, is what allows this lone pair, this lone pair on the alpha carbon to move over and create a pi bond between the alpha and beta carbons. So you have that alpha beta unsaturated, because there are not as many hydrogens here as there could theoretically be, so it's unsaturated. That alpha beta unsaturated acyl-CoA. So, and I'll erase that alpha and beta, positive charge, so it cleans that up a little bit. So ultimately what we've gotten after this first step is FAD has changed to FADH2. And the acyl-CoA has, we've made a double bond between the alpha and beta carbons on that acyl-CoA. That has introduced reactivity into a part of the chain that was not especially reactive before. Okay, so that's the first step, putting a pi bond between the alpha and beta carbons of your acyl-CoA, which is ultimately your fatty acid, just with a CoA attached to it.